We will finish out our study of polynomial functions here in Unit 4 with Section 4.4, Rational Functions. Rational functions are distinct from polynomial functions, but they are composed of polynomial functions. In Section 4.4.1, we will consider an introduction to rational functions. If h of x and g of x are polynomial functions, then a function of the form f of x equals h of x divided by g of x, where g of x is not equal to 0, is a rational function. Now, we've discussed this word rational before, how I can see the word ratio in rational. Ratio means fraction. So a rational function is the ratio of two polynomials. We'll have, for example, a polynomial on the top and a polynomial in the bottom. So the quotient of two polynomial functions makes a rational function. Rational functions have very interesting graphs, as you can see. Unlike polynomial functions, rational functions have breaks and jumps. These breaks are separated by boundary lines. Looking at the graphs below, the boundary lines have special names. On this first example, g of x equals 2x over x minus 2, this graph has a vertical dashed line, or a boundary line, known as a vertical asymptote. It's a strange little word, asymptote. It's not like isotope from chemistry, but asymptote from college algebra. So this graph has both a vertical boundary line, or a vertical asymptote, and also a horizontal asymptote. As we trace the graph, the idea of the asymptote is that this graph continues getting closer and closer to that asymptote without actually ever touching it or crossing it. The same thing is true for our horizontal asymptote. As we follow the graph out to the left, it's going to level out beneath the asymptote. On this side, the graph gets infinitesimally close to that vertical asymptote. Now, the word infinite has the idea of a very large or grand scale, and when we say infinitesimal, that means really, really tiny. So our graph is getting infinitesimally close. That means really, really close to that vertical line. And on this side, the graph is going to level out above the horizontal asymptote. Sometimes horizontal asymptotes are used to describe long-term behavior or some sort of steady state capacity. Looking at the next example, notice we have one vertical asymptote here in blue. Remember, when we write the equation of a vertical line, it is x equals a constant. So the actual equation of that vertical asymptote would be x equals -3. This particular graph also has a horizontal asymptote on the y-axis. Remember, the form for the equation of a horizontal line is y equals a constant. So in that case, it's y equals 0. This particular graph has two pieces, and as we will see in upcoming videos, the domain will also come in two pieces. Our last example here, notice it has two vertical asymptotes. We could write the equations as x equals -3 and x equals 2. And the horizontal asymptote would have equation y equals 1. A graph can have multiple vertical asymptotes, and it may or may not have a horizontal asymptote. When we graph rational functions in this section, our primary goal will be to first locate both the vertical and horizontal asymptotes, and then fit the curvature of the graph within those asymptotes. Now, FYI, graphs can also have oblique or slant asymptotes. So let me give you a quick picture of that. You may have a graph that has both a vertical and a slant, also known as oblique asymptote. So the graph may do something like this up here and maybe something like this down here. For our purposes, we're going to study vertical and horizontal asymptotes only in this section. So stay tuned for more information. They look intimidating, but you might find out that graphing a rational function is even easier than graphing a polynomial function.